Talking about the weakly compressible flows in the atmosphere. Before I do so, let me thank first the organizers for allowing me to come here for a week and speak. I wish I could be here much longer, but it wasn't possible. Let me also thank the British for inventing the Newton Institute on the one hand, and for making great motorcycles on the other hand. That's me on the Nürburgring Nordschleife racetrack.
It's a BMW, isn't it?
No, it's a Triumph. It's a Triumph Daytona. Anyway, okay, let's go. So, weakly compressible flows. I've two sections of the talk. The first is on basically the design regime for unelastic and pseudo-incompressible models, which means they're originally made for relatively small scale studies, cloud formation, etc., so that the characteristic length of the phenomena is about 10 kilometers in the vertical, horizontal, etc., and the associated time scales. So this is what I'm going to be discussing first. How good are they in the regime they're made for? And then I will discuss in the second part a few different regimes that are also of interest and where it's not obvious that they are made for these regimes, and we'll see whether one can say something theoretically about their performance in these regimes. Anyway, this is joint work with a couple of people, Ulrich Achatz, Didier Bresch, Omar Knio, Fabian Senf, Piotr, and Olivier Frau-Louis. And the German Science Foundation is paying lots of my bills, which I'm very thankful for. First, let me motivate quickly. We have multiple scales in the atmosphere, we all know that. And you can get all the nice reduced models you find in the textbooks, such as planetary geostrophic, quasi-geostrophic, weak temperature gradient approximations, Boussinesq, the hydrostatic primitive equations. You can get them all out of one and the same asymptotics-based framework if you're willing to accept a certain distinguished limit, as we call it in asymptotics, which ties the classical dimensionless parameters like Mach number, Rossby numbers, fruit numbers to each other in a functional relationship, introduces basically what you could call the synoptic scale Rossby number as a small parameter, and then do asymptotics on those. And I've summarized all of this in an annual reviews paper in 2010. What turns out, however, to be interesting is that all the models in these bubbles here, in these ellipses, are single scale models. So they have, as a basic assumption in their derivation, you have a single time scale that's relevant, and you have a single length scale in each of the directions, right? Horizontally, of course, possibly different from vertical length scales, but you have in each direction a single scale. This turns out to be different if you want to look at realistic regimes for the design regime of the soundproof models. It turns out that we have to look at a 3 time scale regime asymptotic limit, and that the remaining models, the pseudo-incompressible and unelastic models that I'm discussing, they are 2 time scale models. And I will try to convince you of that and discuss the consequences. So the questions that I could put at the beginning of the lecture is, if acoustics, as we all believe, is not so really important in the sense of elastic acoustic waves in the atmosphere, then what else is the influence of compressibility on the remainder of the flows? And can we quantify it somehow and assess its importance in terms of the small parameters, Mach fruit number, Rossby number, etc., and also of the relevant lengths and time scales, which I'm going to go through in these 2 lectures. And we want to, of course, assess the quality of the soundproof approximations when the acoustics is really not there. So the first chapter here is looking at the design regime, characteristic length scales and time scales of roughly 10 kilometers and the associated advection time. Now first, let's look at the equations. What are we talking about? This is in the design regime of 10 kilometers horizontally, Coriolis is very small, so we can forget about it for the discussion right now. I'll get back to it later. These are the compressible flow equations with obviously the mass balance, horizontal momentum balance, written with the Exner pressure as the pressure coordinate, a pressure variable, then the vertical momentum balance and the transport equation for potential temperature, which for an ideal gas, that I'm considering here, you can write it as rho theta is equivalent to P to the power 1 over gamma, and then that I call a capital P for the time being. Okay, but this is a familiar transport equation. If you insert this here, it's the transport equation for theta in conservation form. So these are the compressible flow equations, and now you get the anelastic approximation by dropping the red term here. You say that the density at leading order isn't changing in time, it's just a function of z. You insert this here, you drop the d rho dt term, and then you have to massage slightly the relation between the buoyancy and pressure gradient terms. This is an additional approximation you have to make in the anelastic model, but then you have it. The pseudo-incompressible model that Dale Durant suggested in 89 works this way. You do not drop the d rho dt, but rather you drop the dp dt term. And then you get the div of rho theta bar times v is equal to 0. That's the divergence constraint in the pseudo-incompressible approximation. And it turns out in that model, you don't even have to fiddle with the pressure gradient and gravity terms. You just let them as they are. You don't approximate the momentum equation any further. This is it. Right? That's what you get. And by the way, the hydrostatic primitive equations come out when you drop these two terms from the equations. Now, let's move on. We want to study the parameter range and the length and time scales of asymptotic validity of this kind of model. So from here on, I'm considering the Mach number to be small. This is the basic assumption of all these derivations. And m is the guy that goes to 0 in the sequence. So now let's discuss timescales in this setting. Obviously, the timescale we are all interested in here is the advection timescale, because we want to see a cloud develop like deep convection, for example, or want the cloud to be advected through the domain. So this is the slowest timescale in the problem. Then the sound timescale, this is all inverse timescales, right? So frequencies. The sound frequency goes like 1 over the length times the sound speed. Whether you take this isothermal or isentropic sound speed, it doesn't matter. The order of magnitude, of course, is the same, right? It's just the factor of square root of gamma. So, and this is the sound frequency. And by the way, g times the scale height is equal to p over rho reference values. I will use that later on, okay? Now we look at the internal waves. The internal waves have the buoyancy frequency as the characteristic frequency, which is this formula, g over theta d theta bar dz, square root. Now we non-dimensionalize. Well, when we non-dimensionalize and take the advection time, which is our primary interest here, we take that as a reference, then the dimensionless frequency becomes unity for advection. Obviously, by the definition of the Mach number, the sound frequency becomes 1 over the Mach number, very large. And here is the non-dimensionalization of the internal wave stuff. So we take out a GH scale from the square root, and we take out we have divided n by uref over h scale, so we have the uref here. The h scale that appears, we split it into 1 square root here, 1 square root there. Then by this operation, we have a non-dimensional stratification term, and we have 1 over the Mach number in front. Right? So that means the internal waves scale like 1 over the Mach number if the stratification is of order unity, which of course it isn't, right? Because the vertical variation of potential temperature across the troposphere is something like 30 to 40 Kelvin, but not 300 Kelvin, which is our reference temperature. So this is not large, which is what led Ogura and Phillips to say, wait a second, if we have this non-dimensionalization and we want a model that has no sound in it, but has advection and internal waves, and we want to do it by systematic asymptotics, somehow we have to slow down the internal waves so they become as slow as the advection. How can that be achieved? Well, we assume weak stratification, meaning we go in here and say the theta bar is almost constant. In the following way, we say the theta bar is a constant plus something that's of the order of the Mach number squared. Well, then in the square root, we have h over theta bar times Mach number squared d theta hat dz. And obviously now the Mach number squared cancels the 1 over m in front of the square root. And on the next page, we see this. Now it's an order 1 time scale. This is what Ogura and Phillips did. They assumed order Mach number squared stratification. They obtained a simple 2-scale regime where they could now use standard arguments of small Mach number asymptotics to derive the unelastic model and that was it. The disadvantage of doing it that drastically is, if you look at numbers, then the Mach number is something like 10 meters per second divided by 300 meters per second, right? This is a 30th, therefore Mach number squared is 1 over 1,000 or so. And if you take a thousandth of 300 Kelvin reference temperature, you are at less than a Kelvin vertical potential temperature difference across the troposphere, and that of course is way too small. This is why the Ogura-Phillips model was criticized heavily. It only works for very weak stratification, was the argument, and in fact the derivation suggested that that would be the case. We are interested in realistic stratification, so we want not a stratification as small as Mach number squared, but we want it weaker than order 1, right? Because when we are at order 1, I showed before, then the internal waves are as bad as the sound waves as far as characteristic timescales go. So we take an intermediate stratification to do that. And what we want then is a soundproof model that keeps internal waves, but they must be fast, allowed to be fast, and we want it to be valid over advective timescales. That's the goal. So now let's move on and make the assumption that in fact the background stratification is weak with some power mu that is not 0 and it is less than 2. If we invert that stratification over here and pull out the m to the power mu from the square root, then the factor that remains is 1 over 1 minus mu over 2, right? So if I abbreviate 1 minus mu over 2 by a new b exponent nu, then on the next transparency we see we have now a 3-time scale regime where advection is slowest with dimensionless time scales of order 1. Internal waves are intermediate with frequencies of order 1 over m to the power nu. And then the sound waves are the fastest and they are supposed to get eliminated. They have frequencies of order 1 over the Mach number. Now, how can we say something about the validity of that kind of model? We take to that end, we rewrite the equations like is often done in rigorous studies of low Mach number limits. We separate out the linearized part from all the nonlinear stuff. And that looks like this. So this is the potential temperature equation written in terms of a perturbation away from our background stratification, as is usually done. Then the nonlinearity of advection of the perturbation appears on the right-hand side. Here's the velocity equation or the momentum equation written in non-conservative form with the buoyancy term, with the pressure gradient term, and with all the nonlinearities collected on the right-hand side. And here is essentially the pressure equation that I showed you before, but reformulated with the Exner pressure instead of this capital P variable as I had it before. But it's just the pressure equation. Now you can see on the right-hand side we have terms that are either order 1 or like this one, they're asymptotically small because nu is less than 1 as it turns out in the regime we're in. So these guys are all small and they become important only over advective timescales. So when this quantity tau here, the time variable, becomes order unity, then the advection terms become important and have a leading order effect. But before we get to that point, that the timescale is order 1, we have two effects that are much faster. We have the sound waves captured by this interplay of the pressure gradient in the momentum equation and the divergence term in the pressure equation. This is what's responsible for elastic waves. And then we have these two terms, namely the buoyancy, the vertical advection of the the background stratification of potential temperature, and the buoyancy term, which are responsible for generating internal waves. And they are multiplied by the different factors of 1 over the Mach number to the power something, depending on whether they represent sound or internal waves. Now the next question is, suppose we start the whole system with initial data that are designed in such a way that sound is basically unimportant. So we have balanced initial data, as it is called in the language, and it is the relevant initial data for the atmosphere because amplitudes of elastic waves are small in general, right? It turns out if we do so, then that means we have to scale the pressure gradient down. It has to be somewhat smaller than assumed here. But if it is of that order of magnitude in terms of the Mach number, then that term will also be comparable to this, and we have the right scaling for internal waves here. We also have to make the divergence term here small, such that it becomes of order 1 over m to the power nu, which means essentially we are adopting nearly unelastic initial data. The divergence of velocity is controlled in the initial data. And from then on, we want to study what happens. We allow for internal waves to develop, and we want to follow internal waves in both the compressible system and in the soundproof system and compare them and see whether they stay close. Both in terms of their internal structure, the way they distribute in the vertical, as well as in the phase, right? If there is a phase difference between the internal waves in terms of frequency, then cumulatively they would depart from each other in phase, and after a sufficiently long time, the phases don't match anymore and the error is order 1, right? So that's the question. How long would, first of all, would internal waves in the compressible and in the soundproof systems be similar to each other in terms of spatial structure? And secondly, how close are they in terms of the phase velocities or the frequencies such that they stay close enough, asymptotically close, even over the time scale of interest? Those are the two questions we want to ask. Okay, let's see. Well, it turns out that there is some justification for doing this rescaling, also to go back to for doing this rescaling and controlling the divergence, because one can show that the time derivatives in the system are actually controlled by their initial data. So if you have an L2 norm, quadratic integral of the time derivatives be small to begin with, it turns out they stay small. In fact, this quadratic integral is conserved in time, which means if you start with slow motions, they stay slow. And that's why prepared initial data is a justified procedure to do, and you don't expect large amplitude to acoustics to appear out of nothing if there wasn't some acoustics to begin with. So that's what we do, and then in order to make very clear where, in fact, does the effect of compressibility come into the equations, we also rescale the time variable and look at the linearized system on the next page. If we do that, something nice happens, namely this is the linearized potential temperature equation, this is the linearized momentum equation, and in the pressure equation we can identify exactly one term, which is the one we had in the crossed out in the pseudo incompressible approximation, namely the time derivative of pressure, which is the one responsible for compressibility. Okay, so we follow the term with the red circle is always the guy in what follows that's responsible for compressibility and makes the difference between pseudo incompressible model and the full compressible model. We follow that. Okay, and then we do something that's more or less standard. We do a vertical mode expansion. We assume the solutions to be traveling in the horizontal as harmonic waves, traveling waves, and have a vertical structure that we have to determine. That's going to be an eigenmode equation. Well, we insert this ansatz into these equations, and then we massage them and try to eliminate variables so that we get a single equation, say, for the vertical velocity structure function W star. You can eliminate other variables, it doesn't really matter. But what you actually end up with is equation of the following type after this elimination procedure. You end up with this equation. Now this looks horrible to begin with, but it isn't. It really is a beautiful equation. This is just minus d dz, forget about this for the moment, times a coefficient times dw star dz. That's basically a second derivative term with a z-dependent coefficient here. Then we have a z-dependent coefficient times w star, and we have the eigenvalue here encapsulated by 1 over omega squared, the frequency squared, times a different vertical structure function times w star. This is a Sturm-Liouville problem. And if you forget about compressibility and remove this term, it's really a regular, classical, standard Sturm-Liouville problem. We know everything about them. Namely, for example, that they have a nice set of eigenfunctions that are mutually orthogonal under a weighted scalar product, right? So they don't interfere with each other. We know that the eigenvalues stay away from 0 with a finite distance, which in fact the highest frequency we can have is the Brunt-Väisala frequency. So they stay away from 0, and then the omega becomes slower and slower, meaning that the factor here becomes larger and larger, in fact goes to infinity, with finite separation from one term to the other. In fact, if you take the mode number, the number of crossings of 0 of the eigenfunctions in the vertical, as being m, the mode number, then the eigenvalues increase, the 1 over omega squared increases like mode number squared. So all of this is known, and it means that the pseudo-incompressible model, which we obtain when we cross this out, has beautiful internal waves that we can completely characterize. Well, by the way, if you go and assume, adopt the compressible case, you say that this is non-zero, you have two options. One option is to say, let's assume we had eigenvalues that are close to the pseudo-incompressible eigenvalues that we obtained when this wasn't there. We know this is an order 1 number, and this becomes only smaller if my mode number goes up, which means that this term is really of order m to the power mu and much, much smaller than 1, so this always stays positive. And it turns out you can rigorously prove that the compressible eigenmodes differ from the pseudo-incompressible eigenmodes by a term that's of the order Mach number to the power mu. So that's a nice consistent expansion. The compressible modes look very similar in spatial structure to the pseudo-incompressible modes. So that's what is result number 1. The spatial structure is the same. By the way, now this is a nonlinear Sturm-Liouville problem because the eigenvalue appears in this and this place nonlinearly, but you can do an iteration procedure to in fact prove that that the eigenvalues stay close by a term proportional to Mach number to the power mu in a kind of Picard iteration procedure. Now, if the eigenvalues stay close of order Mach number to the power mu, then it means they are not the same. And it also means that if I have a wave traveling in the compressible setting and have another wave traveling in the pseudo-incompressible setting, they don't move at the same speed. There's a speed difference of order Mach number to the mu, right? And if I let them go, they will slowly separate because of that phase speed difference. Now we want to achieve that the phase difference is still of order 1 when we reach the advective timescales. Because then we can say our model is valid up to advective timescales. And it's easy to calculate that if you take a phase difference of order Mach number to the power mu, and now you take internal wave times of order Mach number to the minus nu, right? We had rescaled our time coordinate, and Mach number to the power nu was the difference in the characteristic scales of advection and internal waves, right? And so we want that in the limit when they just start to split apart by order 1. This, in fact, is 1. So that means mu minus nu is equal to 1, and that means mu minus, this was 1 minus mu over 2 is equal to 0, sorry, of course 0. This is equal to 0. And when you solve it, this is obviously 3 over 2 times mu minus 1 is equal to 0, and there you go. You have a limit. Mu must be larger than 2/3 in order to make the phases still match when we reach the advective timescale. But we can allow for stratifications of the power Mach number to the 2/3. And when you now insert numbers, Mach number being a 30th, and you check what comes out in terms of vertical stratifications, you can go up to 30 to 40 Kelvin, no problem. Okay, so that justifies in the design regime of the pseudo-incompressible model, and in fact, when you do the analysis, it turns out the unelastic does the same. Yeah, the deviations are in different terms and appear in different locations in the equations, but the order of magnitude of the error is exactly the same. So the pseudo-incompressible and the unelastic models, they are valid approximation in this formal asymptotic sense on advective timescales if the stratifications satisfy this relationship of being less than order Mach number to the power 2/3. And that allows for realistic stratifications. Good. Right. This is eigenmode number 10. It says somewhere, yeah, W10. This is the vertical velocity eigenmode number 10 for the unelastic pseudo-incompressible and compressible models. And in the picture norm, you can't even distinguish them. Yeah, they are even more accurate. The epsilon I picked here, Mach number to the power mu was 0.1. Yeah, but they don't differ by 10%. They differ by something like 10 to the minus 3 or so. And the reason is, if you go back, I can explain it to you. Oh, no, I'm going the wrong direction. The reason is the omega becomes smaller and smaller the higher the mode number. We know that. The more stratification you have, the slower the internal waves. And so when the mode number becomes smaller, this term becomes smaller, which means that this compressibility effect becomes less and less important. And this is why for relatively high mode numbers beyond 2 or 3, the pseudo-incompressible and compressible models agree even better than the estimate would suggest of order Mach number to the power mu, just because they become so slow. Right? Okay, so we have that. This is in terms of the eigenvalues, the same conclusions. For two different horizontal wave numbers, we see that sometimes the unelastic wins and sometimes the pseudo-incompressible wins, but the differences are all very small in terms of the eigenvalues. We have run a simulation. Piotr did that we initialized the an Eulag simulation with the eigenmodes I computed from the Sturm-Liouville problem, and it produces a nice traveling wave. So this is all consistent with a full-fledged code as well. We've also tried it with a compressible this spring, and that worked indeed also. In Exner, yeah. Okay. Now, let me skip that for the moment. This is for Tommaso's lecture tomorrow. We have a code that does with the same one and the same numerics on all the three models: unelastic, pseudo-incompressible, compressible. And when you do this breaking wave test that we have seen in Piotr's lecture also before, basically you see hardly a difference. If I go back to this last slide here, you have a pseudo-incompressible simulation up to a point where the wave hasn't broken yet. And you compare that with compressible simulations, either with a CFL number for advection that's of order unity, which is what you would also use in this model, naturally, or you compare it with a compressible simulation where the time step is chosen acoustically. It's all the same. It doesn't matter, right? When there is no acoustic modes to begin with, a good code that's reasonably built will not show much of a difference, and it shouldn't according to the theory. Okay, this will be very brief, and then we have a short discussion. What we need to show is that this system here, in fact, rigorously in a mathematical sense, doesn't produce any deviations and hiccups like singularities and blow up of derivatives over the advective timescales. That means we want to show that the fast system, first of all, produces smooth solutions over timescales independent of the Mach number. Then we can let it oscillate up to timescales of advection, and then see how does the advection interact with the gravity waves. And there is an obstacle here in terms of theory that has to do with the fact that in order to show this smoothness, you typically go through energy estimates and Sobolev norms, etc., and you want to control high enough Sobolev norms of the solution. And the coefficients, unfortunately here, the theta stratification is non-constant. So you have a non-constant coefficient oscillatory system, and that's not a trivial thing to control the derivatives upon. But we think through the spectral expansions and some other tricks that we found, we can control them, and then we are hoping to be able to prove this. But that's for another talk. Right, summary is, so I discussed that unelastic and pseudo-incompressible models are made originally for a certain regime, 10 kilometers, 20 minutes. Within that regime, they don't, neither wins over the other. They are both equally valid approximations. And they are, in fact, valid approximations in a formal asymptotic sense for realistic vertical stratifications that we find in the troposphere. Maybe not in the stratosphere, but I'll get to that. And that's the first talk. Thank you. Yes.
So Rupert, did you do it for the unified system as well?
What is that?
Did you do it for the unified, this unified system of Arakawa and Konoha? Does it fall in the asymptotic analysis in between?
That I haven't
kind of, or
tried yet.
Is it an outlier, or?
I haven't tried that yet. No, I haven't tried that. But I know that for this design regime part, it comes out to be the unelastic model, right? So in that sense, it falls into that class as well. It wouldn't change the picture here. No more questions? Then let me just go on. So number 2 is all particular scaling regimes and thermodynamic consistency. This is again work with, I was planning that to be the second talk, and Hillary told me that possibly some people won't have seen the first talk. So some of the slides I will skip over quickly because you have seen them already. Like this one, and this we have seen, and this we have seen. And the design regime we have checked, and now we go to small engineering scales. Okay, this is like meters instead of kilometers. To understand what's going on, let's look at the equations again. This is the form I showed you before, where everything is basically in some way some kind of conservation form, right? For the transport of potential temperature, and when we want to go unelastic, we cross out this term, the d rho dt term that would be there. If we go pseudo-incompressible, we cross out the dp dt term that would be sitting here. And so this is the in conservation form, the pseudo-incompressible model. This is essentially the unelastic model. Now, the key difference that is often, you see that cited in the literature quite a bit, the key difference between the two models becomes obvious when you write them in non-conservative form like I have done here. So we keep the divergence constraint. We use this divergence constraint in simplifying the momentum equation to get this expression, right, in velocity form. And we just use the definition here of theta and rho bar theta in capital P to write the advection equation for potential temperature. The same we do down here. And then it turns out that the following happens. There's two differences. One is, of course, a difference in the divergence expression. The rho bar and the p bar, they differ by a factor theta bar. And theta bar is not constant, but has this order Mach number to the 2/3 deviation maximum. So they are similar, close, but they are not identical. The more important difference for the present purpose of looking at small scales is this. In the pseudo-incompressible model, the pressure gradient term is multiplied by theta. And theta is a function that evolves in time and space. It has perturbations. So you have a time and space dependent coefficient sitting here. And obviously, if you have a gradient of theta pointing this way and a gradient of pressure, say, pointing that way, you get a cross product and you generate vorticity. That's the baroclinic vorticity generation that is incorporated in this version of writing the pressure gradient. That is absent in the unelastic model. It doesn't have that term. It only creates vorticity from horizontal variations of the buoyancy term. Okay, so now let's see how important that is on small scales. And for this, I went to the limit, where basically the background P and the background rho are constant. Then we have incompressible flow in both cases. But we maintain this difference, that on small scales, we have essentially a factor of 1 over rho grad pressure. And the buoyancy is driving the flow. And here we have no 1 over rho factor. And when you now take an example of a falling cold air blob in a otherwise quiescent environment and follow the evolution, you get the following. This is the unelastic setting. This is the pseudo-incompressible. The bubble was sitting up here in the domain, which is, by the way, 10 meters by 20 meters. So this is a small scale. And you let the cold air bubble, which is in this case 10% colder than the environment, you let it drop. For the 10% variation, the results look basically the same. There's no difference. If you go to larger differences in density, like 50%, you begin to see differences. This looks almost the same. This one starts to concentrate. And when you go to very large differences, like 90% density difference, you can see that the pseudo-incompressible model does what we would expect, namely a cold, heavy blob of fluid should drop like a droplet. And it should not be distorted much by the environment, which cannot come up with any resistance because it has no mass. Right? So that's what happens here. But in the unelastic setting, it doesn't happen. And the reason is just what I said. The potential temperature has a strong gradient here in this direction, normal to the surface. The pressure gradient, obviously, is along the surface because you have to accelerate the fluid around it, which means the pressure gradient goes this way, the theta gradient goes this way, you generate a lot of vorticity at the interface. And in fact, this is what allows the fluid to zoom around the bubble and let it drop like a droplet. And that generation of vorticity term is simply absent here. It doesn't work. And this is why in the unelastic model, or in the limit, which is the Boussinesq model, you see this weird distortion of even a heavy bubble in a very, very light environment. Right? So here we have 0, 1. The winner is the pseudo-incompressible model because it represents the heavy particles more appropriately. If you wanted to take an unelastic code and go to large density differences, you don't get the right answer anymore. You might not want to do that and not use the code for that, then you're fine. But if you want to use it for that, you better be pseudo-incompressible.
Rupert, can you go back one slide?
Yeah.
Yeah. Are they non-dimensional? Is the system non-dimensional?
Yes, but it doesn't matter here because I've thrown out the parameter, Mach number parameter. Okay. Yeah. Right. But you wanted to say something?
Yeah, there is another effect I found accidentally that never thought about this before. That when we go to those like a very small outward numbers, right? That density aspect. Then in the unelastic system, effectively the acceleration, buoyant acceleration can grow unboundedly. Whereas in pseudo-incompressible, like in a fully incompressible, it's limited. To the just G, right?
Okay.
In a limit, it becomes.
I see.
G.
I see.
And I found it hard way.
Interesting. Yeah. I would be interesting to work that out on the equations. You had a question?
You said the elastic approximation reduces to Boussinesq, so you can expect. I mean, basically, you have inertial terms which are missing in the dense path. I mean,
well, but I don't. You can interpret it in different ways. But what I found mainly missing when I write it this way is just the prefactor here.
Sure, but if you fold it back, and I mean, it comes back down to the Boussinesq approximation, neglecting the density variation in the momentum,
right,
or in the inertia.
Yes, right.
So you have initial term
happening right here. That's right.
Yeah.
Yes,
Yeah.
I agree with you.
Yeah.
Yes, exactly. Yeah. Okay. So that was this regime, 0, 1 for pseudo-incompressible. Let's look at long wavelengths. It was you find it in Davies et al. 2003, who were cited yesterday too, that the soundproof approximations become unacceptable and deteriorate when you look at very long wavelengths horizontally. Let's see what the theory, so far as I have driven it up to this point, says to this. It says Well, you have seen this. I did the ansatz in the vertical decomposition, and I did the Sturm-Liouville problem, right? Now let's look at the Sturm-Liouville problem. And here we want to look at small lambda limits, right? Lambda is the horizontal wave numbers. We want it to be small and see what happens. So I've colored it here. So this is the lambda where it appears. And now look at this. We call lambda squared over omega squared, which appears here, and inverse of it appears here, capital lambda. And then we let lambda go, the little lambda, the horizontal wave number, go to 0. What happens is that we get a Sturm-Liouville problem of regular type that contains the capital lambda parameter, and it is independent of in the limit, independent of the horizontal wave number. And the logics that tells us that the eigenvalues for the compressible mu m equals 0 case and the pseudo incompressible m equals 0 case and the compressible case, that these are close to power m Mach number to the mu, still holds. There's no difference in the argument. So if you keep the stratification weak enough, as we assumed, Mach number to the power mu, then you can have as large horizontal wave numbers as you wish. It doesn't make a difference. The accuracy remains the same. I haven't considered Coriolis so far, right? Let's include Coriolis next. When we include Coriolis, something magic happens, and I just discovered that 2 days ago, trying it, because I wanted to say something new to the guys who always listen to my talks. And this might be known to many of you who have been in the field for longer. But what I discovered here in this case, if I go to the F-plane, so I neglect for the moment the horizontal variation of the Coriolis parameter, then basically I can rewrite my Sturm-Liouville problem in terms of a new scaled horizontal wave number parameter, lambda star, which equals lambda, the real lambda in the eigenfunction, divided by 1 minus f over omega squared, and I get exactly the same eigenvalue problem I had before. So I get the same vertical structure functions as I got them before, with the same eigenvalues here, except that when I want to insert and evaluate, I have to do the physical wave number, the real wave number in space, has to be computed from the lambda star by this formula. But again, the same holds as before. The arguments that tell us that the compressible and pseudo-incompressible modes are close to each other are again the same. So the accuracy remains again the same, provided the stratification is weak enough. This, by the way, again goes through for unelastic and pseudo-incompressible, which is why we have 1 to 2 right now.
So what would happen if f would become like equal to omega?
This shows nicely that it isn't going to happen. What happens is that f omega is bounded from above by f, which we all know, right? The eigenvalues, they don't go, they're limited by f. You see that in all the dispersion graphs, right? And this is exactly what happens here.
So the faster I start rotate, okay, I understand. Years ago, we did those experiments on a very tiny planets that we were accelerating rapidly, and the waves, they were changing. The gravity waves were changing in response to the rotation. Something like that.
Yeah, it has to happen.
They're called Poincare waves then.
Yeah. Right. Yeah. And the next is, right, I have the Coriolis. Right, we checked that. So we checked long waves, including the F-plane approximation. When I go to the beta plane, or even to the sphere, of course, the analysis is not as straightforward anymore, because then I would have to include non-trivial eigenfunction expansions in the meridional direction, in the direction in which the Coriolis parameter is changing. So that I haven't bothered to do yet. Now let's look at something completely different, internal wave packets of very short wavelengths that are traveling upward in the atmosphere and break up there. My friends from Frankfurt, Ulrich Achatz and Fabian Senf, they are very interested in these breaking waves in the stratosphere. And one thing you have to take into account for these is the stratosphere is almost isothermal above the tropopause, right? And isothermal stratification is not in that limit, in that asymptotic limit of small Mach number power something stratification. At least if you are not willing to go to assuming that gamma minus 1 over gamma is small compared to 1. This is often called the Newtonian limit, and you can make the asymptotics work even for isothermal stratifications, but only if you again take that coefficient here, which is R over Cp, tie it to the Mach number with an appropriate power. But if you don't want to do that and say this is a pretty drastic assumption to start twiddling with the thermodynamics, then the isothermal is not within the asymptotic regime I've discussed so far. Okay? So we're looking now at strong stratification for what we did, and we allowed for isothermal, and it was this kind of a breaking wave that we were interested in, and the next that happens is the wave breaks, right? Okay. What we did here was a WKB type expansion to look at what a wave packet does that travels vertically. And notice that the expansion here is not a small amplitude expansion. We expanded around a state, or we allowed for perturbations in the short wavelengths where the velocity is comparable to the leading order background velocity, and the scaling was such that we can see in this regime the waves overturn. So this is really what you would call a nonlinear regime, and it only linearizes because internal waves are shear waves, and then the nonlinearity only comes in at higher order. But notice this is really not a small amplitude expansion, it's a short wavelength expansion, which is conceptually very different. And we had to battle the reviewers on this quite a bit until they understood, wow, they're doing really a nonlinear thing. Anyway, so what you can do then is do the standard WKB for the leading term here. Then you can explicitly pull out the nonlinearities in the next order up to wave number 2. And of course, you can pull out the interaction between the short waves and the background flow. And to make a long story short, what happens is that pseudo-incompressible and elastic both get the dispersion relation right on short wavelengths. Actually, they should, because on short wavelengths we have no large density variation, both reduced basically to Boussinesq. And then you have the classical dispersion relation of Boussinesq theory on the small scales. Accordingly, the ray tracing equations come out the same. A wave action conservation law comes out the same, but the wave mean flow interaction is different, interestingly. When you want to know how a breaking wave or a nonlinear wave that travels upward changes its own background flow, there suddenly in the compressible and pseudo-incompressible equations, an additional term appears that has to do with the average square of the buoyancy term, which is there in the compressible, pseudo-incompressible, but not in the unelastic model. So in this case, the wave mean flow interaction stuff, this is, by the way, here the acceleration of the horizontal mean flow. This is the vertical momentum balance for the within the wave packet, averaged over the wave packet, and this is the vertical velocity equation coming from the divergence constraint. Anyway, so in the equation that determines the pressure field that drives the mean horizontal velocity, you have a new buoyancy term coming up that's coming from the average over nonlinearities.
But typically it's small. This is small term.
Well, in the asymptotics, it's an order 1 term. It's as important as the others. Okay, right, and then, so in this case, at that last minute, it's literally the last page in the paper, the unelastic loses, and we have 1, 2, 3. And Felix Rieper implemented test cases with a full pseudo-incompressible model to compare the WKB theory with a full implementation. And for the mean velocity development in such a wave packet, he got, in one of the test cases, very good comparison. For the effective buoyancy terms, he got reasonable, and for the pressure gradients, a relevant one that drives the horizontal flow. You can also see the structures are very similar. So that was for leading order stratification. realistic stratification for the stratosphere, and so the WKB and the pseudo-incompressible also agree reasonably well empirically when you really compare direct simulation with the WKB. Okay, last topic. Thermodynamic consistency. So in soundproof models, the mechanical energy essentially decouples from the thermodynamics, right? Because what you do is that the energy, when you write the total energy as the sum of thermal, kinetic, and potential energy, then by the assumption that you have a background stratification that doesn't depend on time, the leading term here is basically a function of Z only, and that's where the decoupling takes place. And you can only shuffle energy from kinetic to potential, but you have a hard time accessing or you have no chance of accessing the thermal energy. That happens in the unelastic, in the pseudo-incompressible model, as Dale Durand showed in his original derivation. But you do have an energy conservation law of exactly this type, and so that basically is satisfactory. The energy of the model cannot go haywire when you run it for a long time. Now, this was all done for an ideal gas equation of state, and then what happens when you have diabatic flows and you have general equations of state? Can you still use it? And Olivier Paul-Louis in 2008 looked at the unelastic approximation, and he required that there is an energy conservation law, which in the case of diabatic source terms and maybe source terms of moisture, would be consistent thermodynamically in a sense that you have a physically meaningful thermodynamic potential here for the entropy and a what is it called, chemical potential for the species quantities that are related to physical variables in the right way, and that end up producing entropy when you run this thing forward. And he showed that if you assume a homotropic background state, in fact, he went back to Ogura and Phillips' regime, where the stratification is order Mach number squared. If you adopt that regime, then you can in fact show that that kind of conservation law is satisfied. If you include in the energy flux the perturbation pressure, the elliptic pressure that you have to solve for in a unelastic model, and then basically everything is fine. The energy, the enthalpy, the temperature, and the chemical potential all come out to be the expected ones, namely the ones you get when you invert the entropy, the current value of your species, like moisture, and the background pressure. Just constrain the pressure to be the background pressure, then everything is consistent, as was expected. Then Olivier told me at some point, I can't do it for the pseudo-incompressible, it doesn't work. And the reason was that the pseudo-incompressible model up to that point was always discussed in terms of, I don't show it here, I have it on my previous slides. I introduced the Exner pressure, remember? It was theta times gradient of pi that appeared in the velocity equation. And this is something suddenly tied into the formulation of the pseudo-incompressible model, the way Durand derives it. And that was responsible for making everything happen thermodynamically in his analysis of the, I showed it here, in this analysis of the diabatic case. Now, when you go to general equations of state, the Exner pressure has no meaning anymore, at least as far as I know, because it really is some special definition you get from the constant specific heat properties. So if you go back to real pressure, you have to work harder. And then Olivier and I worked it out. What happens is you again can get a consistent energy equation with meaningful thermodynamic and chemical potentials, where again the energies and etc. are with a single star. They are all the expected ones, except for the fact that you need to include in the chemical potentials here, you need to include the perturbation effect of the elliptic pressure. Which makes this a sort of interesting system. And what it means in terms of the equation you actually have to solve, if you do not do the pseudo-incompressible with the Exner pressure, it means you have to use this equation. So there is the transport equation for density again, as before. Now you use not the Exner pressure here, but you use the physical pressure. then you have to include in the buoyancy term the effect of what happens here, the delta P. Okay, so this includes the background pressure gradient as well as the gradient of delta P, but the delta P perturbation induce the effect on density of the pressure perturbation, the elliptic pressure perturbation. You have to include it in the buoyancy term, otherwise it's not thermodynamically consistent. But if you do, you get a good, nice thermodynamic consistency. And so here is the pressure decomposition. The delta P appears, and the divergence constraint is a subtle one, because now you know that the rho star is the original density evaluated at entropy, moisture, and the background pressure field. And so how to solve this, actually, we don't know yet. It's not a straightforward divergence constraint as you had it before, like diff of something is equal to 0. It comes out in a much more subtle way, and Warren O'Neill, another student of mine, is working on implementing that. All right, that was that. And since this pseudo-incompressible model actually gets a thermodynamically consistent formulation even for strong stratification, order 1 stratification, pseudo-incompressible wins once more, right? And I have an end result of 1 to 4. Right, and that gets me to the end. The summary is in the design regime, you can use either unelastic or pseudo-incompressible. On small scales, you can use unelastic only if you accept that density variations are small. For long waves in the F-plane, both are very nice. For short wave packets in strong stratification, unelastic doesn't produce the right mean flow wave interaction, while pseudo-incompressible does. Thermodynamically, you can use an unelastic model. It might actually be that you can show thermodynamic consistency for unelastic even in strong stratification, but I haven't found a way to do it, and neither has Olivier. But that challenge is open. I don't want to exclude it, right? But right now we don't know. But for pseudo-incompressible, we could show it for strong stratification. What's open is what happens when you look at long waves on the sphere. So when the Coriolis variation comes back in, like in Davis et al. And what happens when you look at deep atmospheric modes in addition, which I haven't done so far either. And the truncation errors noticed are of order epsilon, where epsilon is the stratification strength. In the third case, it's the Mach number for cases 2 and 5, and it's the length scale ratio between the wave packet oscillation wavelength and the background length scale for case number 4. So differences remain between compressible and the soundproof models, and they are of the order typically of a tenth or so, formally in the asymptotics. You get lucky with the internal waves because they slow down the stronger the variability of the wave is in the vertical, as I showed before. But formally, in terms of asymptotics, you don't get better than the 10% that we have in this epsilon. Okay, that gets me. There's a couple of references. Anyway, this is the end. Thanks very much.
Apologise, I was too late to introduce you.
Oh,
It wasn't
no problem.
necessary.
So about those overturning waves, you know, Joanna.
The what? The
overturning waves.
Overturning waves, yes.
Comparability of the incompressible and elastic.
Yeah.
So Joanna and I will do those calculations purposely to see the numerical realizability of this result.
Yeah.
And she showed yesterday some of those. This was for isothermal atmosphere, in the stratosphere, and so on. So we found that for normal conditions, stratospheric conditions, that those differences are negligible. However, when you go to the actually density scale and potential temperature scale comparable, actually potential temperature scale slightly smaller than density scale, then you can see the difference. And the difference is that it makes sense because an elastic approximation tends to overturn waves more vigorously because it's more linear. So theoretically, can you tell that this extra term has an opposite sign than the regular buoyancy term? Because this is the difference, right? So this is like a This
No, the extra term, the difference is not in the dynamics of the wave packet. That's all the same. The difference is in the wave mean flow interaction. Okay, so how does the wave packet accumulate vertical momentum and buoyancy in order to set up a different pressure field that then drives the horizontal large-scale flow? There is a difference that occurs, which you haven't even looked at probably when you just focused on how the waves overturn. This should all be very close.
So you need to
according
look for
theory
like
as well.
Reynolds stresses, things like this, yes?
It's similar to that, except of course this is an analytical closure for something like a Reynolds stress in the special case of a modulated harmonic wave packet.
On the same subject, actually, but we simulated the direct numerical simulation of the Plummet-Ewan experiment, which is driven by wave mean flow interaction, and that's like strong stratification of like the stratification is caused by the salt in the water.
Yeah.
So you layer basically the salt, and we used the Boussinesq equations for that,
Yeah.
and the results were coming out very well. How does that tie in with?
Well, in water, no doubt, because the density doesn't change much vertically, right? Essentially, it doesn't change vertically, period. So then the
No, but
divergence
the density
constraint-
change is created by creating layers of salt, increasing basically the salt.
Yeah, but these density changes are minute relative to the background density. And what makes the divergence term and the
So that's
difference,
still in the weak. This you're saying this is still in the weak.
the small scale
regime,
limit.
basically.
It's in the small scale limit for small density variations, and I would not expect big differences there at all.
Can you go back to the small scale limit
Yeah.
of the equation? So the equation, I mean the zero Mach pseudo incompressible is you boil it down to incompressible Navier-Stokes.
Yeah, no, well, I've not discussed the friction terms here,
Yes,
but
the
it
incompressible
boils
are
down to
enough.
the zero Mach number limit, incompressible limit. Yes, exactly.
Yeah,
That's
yeah,
what it
okay,
does.
yeah.
Yes.
No, we talk about this. I have this puzzling result on the planet that when we do baroclinic instability, that actually this is the case that anelastic agrees very well with standard hydrostatic primitive equation case, and the pseudo incompressible goes wacko, like develops instability twice as fast as nothing like this. They still don't understand this. It's puzzling.
Right. Yeah, I've said this. What happens on the sphere and what happens for deep atmospheres, I don't know yet. As I said, also when we compared the eigenvalues and eigenfunctions for the simple internal wave cases I've shown, it's somewhere. Yeah. As you can see, for where are we? Anelastic. In the case of small wave numbers, it turns out that for low mode numbers, the unelastic turns out to be better for some reason than the pseudo incompressible. This is a subtle cancellation of terms. And maybe this happens more systematically for the test case you looked at. In that case, this maybe the reason is hidden there.
Anelastic has one important numerical advantage. Is the fact that you don't have this extra coefficient in front of the pressure gradient makes operator much better condition. So it's a practical.
But the coefficient isn't varying so much.
Well, when we go to very strongly stratified media, that makes a big difference.
Yeah, okay. But I would even dispute that. If it's just the stratification and the potential temperature is stratified strongly, I think that can be taken out by preconditioning.
Yeah, we do, but
if-
you need to have
if
better
the theta,
preconditioning.
however, has strong variations in space and time, then I see how it becomes much more
Yeah,
difficult.
but it takes better preconditioning.
Yeah, that's right.
Mhm.
Thank Rupert once again.
Okay.